Next up, we have Jean-Louis Diascorn from Harmonic. He'll be talking about how AI technology is dramatically improving video compression for broadcast and OTT content delivery. Jean-Louis is a senior product manager for compression encoders at Harmonic and previously at Thomson Video Networks. In his current role, Jean-Louis leads the use of AI in compression. Prior to 2006, Jean-Louis designed content protection systems and contributed to the ATSC specifications in conditional access and PSIP. Oh, so you're the one to blame. At Thomson Corporate Research Center, now Technicolor. I love PSIP, don't get me wrong. During 7 years as a design engineer, he worked on some of the first SD and HD MPEG-2 encoders in the world. Jean-Louis holds a graduate degree in electrical engineering and computer science from the Polytech Nantes in France and has been awarded several patents in content security and compression. So please come up, Jean-Louis.
Thank you, Thomas. It's a pleasure to be here today. Glad to come back to LA. Last time was for the marathon, but don't worry, I'm sure I'll be much faster. So here today I'm going to present you in this talk how AI technology is dramatically improving video compression for broadcast and OTT content delivery. So I'll do that with 3 examples. First, let's look at the agenda. First, I'm going to present you the approach that we used. This is a 2-step approach. Then we'll look at the 3 examples. First, the dynamic encoding style, then the dynamic resolution encoding, the third, the dynamic frame rate encoding, and we'll also look at combining them with combining several applications. And I will end with the possible future evolution of AI for video compression. So in fact, video compression has been around for many years, more than 20 years. And a lot of improvement have been made, different standards, but this took a long time, took a lot of effort. Now there is a new way of making improvements. We know that AI, it's very good at predictions, at decisions, and this, in fact, is very useful and very impactful for video compression. Let's look at the model that we've used to implement the 3 examples that I'm going to present further. This is the concept used to implement AI for video compression. The 2-step approach includes first an offline learning process. This is the top of the picture, where we feed a lot of test files to an offline learning system. And this can take hours, days. And it produces a prediction model. This prediction model is then downloaded into a live system. This can be like a software download. And the second step is running the live system. And the live system will use the prediction model to produce a better compression, if you will. Let's look first at the, in terms of examples, at the dynamic encoding style. Well, as you know, video compression is mainly about reducing the bitrate and maintain or increase the VQ. So this first example is just about that. How can we improve the bitrate, reduce the bitrate, and keep the quality? Let's look at the architecture of this encoding style application first. This is the 2-step approach I presented before, and here employed for the encoding style application. So you have all those test files and providing encoding styles, and we have video analysis as well. The encoding style are, in fact, encoder configurations, different encoder configurations for the encoding core. And many of them are provided here to the AI system. And after so much time, it produces an encoding style prediction model. This encoding style prediction model is downloaded into the live system. Then when it's running live, this is the second step with video. The same video analysis will provide information to the prediction model, which in turn will modify the encoding core. So you will note here that the encoding core is, I would say, a normal encoding core. So we're not adding steps, or we're not making the encoding longer. It will have the same latency as a normal encoder, but it will just be better tuned to produce a better compression. So yes, here with the encoding style application, we're looking at bitrate reduction, and this has been deployed at a tier 1 satellite provider. And what we've observed is, on average, about 20% bitrate reduction on a variety of content. When applied to OTT, encoding style can also be named content-aware encoding. Let's look at the second example now, the dynamic resolution encoding. Resolution is about picture quality, for sure, but for low movement video, you certainly want to have the highest possible resolution. This is where the human eye will be able to see many details and we'll see all the differences. On the other hand, if there is a lot of movement, well, the eye, first of all, will not maybe be able to see all the details. And also, these movements make the encoding more difficult and could generate artifacts. So it can be useful to have a lower resolution picture. This is what this dynamic resolution encoding does, selecting with AI the best possible resolution at any time. Again, let's look at the architecture. First, the dynamic resolution encoding with AI-based quality of experience. The first is the same approach with the first step. This time, the test file and the element feeding the AI include many encoding cores which are running at different resolution. So many resolutions are fed into the AI, video analysis is fed into the AI, and then at the end, you get dynamic resolution encoding parameters, prediction model. Again, this prediction model downloaded into the system, but this time, depending on the video, this prediction model will select which resolution the single encoding core should run at. Here, the application is for mainly OTT. This is where it applies the best. And the benefits are CPU saving primarily. You might ask, is it possible to combine several examples? Here, you can say yes. Here we're combining the dynamic encoding style or container-aware encoding for OTT here with dynamic resolution encoding. If you look at the left of the slide here, the legacy CBR static profiles. As an example, we have 3 profiles for OTT, 4 meg, 3 meg, 2 meg. First one is 1080p, the second at 720p, and the lowest one at 480p. These are running at constant bit rate. So in some cases, the bit rate is very high, in fact. And it uses several profiles, so a lot of CPU. So this works but it's quite inefficient. High bit rate, high CPU. If we add content-aware encoding on top of that, this is the picture in the middle, then the content-aware encoding will be able to reduce the bit rate, when it's not necessary. For example, the picture in the middle is more documentary, uses less bits than the sports. We can dramatically reduce the bit rate, even for 1080p. In this example, for example, all the profiles go down below 2 meg per second. And then the last on the right, combine content-aware encoding plus the dynamic resolution encoding controlled by AI. And here, you get the best of both worlds. For the sports, a lower resolution is used, so using less CPU. For documentary, the lower bit rate, but high resolution. So you get together lower CPU and better video quality. Let's dive into more details about the results of the dynamic resolution encoding with the statistical analysis of long duration content with dynamic resolution solution. Here we're showing the percentage of duration using a different resolution than the nominal service profile. Our nominal service profile for this first graph is the SD case, the 480p at 1.5 megabits per second CBR. So using dynamic resolution encoding, in fact, you see that about only 20% of the case, it's non-nominal resolution which is used. All the rest is at higher resolution, meaning better VQ, better visual quality. And this is still at the same bitrate 1.5. If we look for the same type of content, sport for HD now, with our nominal profile at 1080p 3.9 megabits per second, it's about 30% of the time the nominal resolution is used, and the rest is at lower resolution. So here we will save on CPU because we are not using the high resolution all the time. Let's dive further deeper into the results. Here we're showing the 480p at 1.5 megabits per second nominal service with more details. On the top left, it's the graph I just showed before, the sport. And in fact, this graph was generated with, and the result comes from the AI configure where when there is a slight variation in VQ, the machine decides to change the resolution. And in fact, it can be tuned differently, where in fact you allow the change in resolution only if there is a visible change in VQ. This is what the delta 03 VQ means here. This is the threshold of visibility on a MOS scale 0 to 5. So in that case, we see little difference going from 20% of nominal resolution to 30%. So same ballpark range. We did that on several other content. Here we have another example at the bottom of the slide, the entertainment video. With the entertainment video, with the slightest VQ change, we're about 10% low resolution. So great improvement in video quality, certainly. And then when moving to a visibility threshold, we get about 70. So again, not major change. So you think it doesn't matter. Well, let's look at the HD case now. HD case, where our nominal is 1080p at 3.9 megabits per second. Here we have on the top left the previous graph we had before, where 30% of the time we are at the right high resolution, the rest of the time it's lower resolution. If we change the configuration now of the decision to a visibility threshold, well, the 1080p is used 63% of the time. So this is a big change this time. And looking at other type of content, on the bottom of this slide, it's the entertainment video, going from 43% of 1080p to 78%. So it will matter. So now, depending on the decision that you need to make, either save on CPU, certainly on the left here you will save more CPU, and or on the right, you will want to keep all the time the same resolution. So it means that it's important to make the right choice when using such type of AI-based encoding. Further results details final result on dynamic resolution. For complex content, complex movement, we found 50% CPU saving. And for simple content, we found 40 to 50% CPU saving. So it's quite significant. Let's look at our last example of AI applied to video compression with dynamic frame rate encoding. A little bit like the previous one, but the other way around. At high movement content, you want to have high frame rate. This is to avoid any jitter that can sometimes be annoying. But then, if there is very little movement, why spend all the bits or why spend all the CPU encoding every frames if in fact there's very little to encode? This is what this last example does, using AI to select the most appropriate frame rate for the video. Using the same two-step approach here. So test file, this time we're using several or many encoding cores at different frame rates, video analysis, feeding AI, producing a prediction model. And again, prediction model downloaded into the live system, and this time it will select the right frame rate. The application of the dynamic frame rate is all type of delivery methods, satellite, OTT, IPTV, cable, and terrestrial. It will save on a CPU, as I said, mainly, and a little bit on bitrate as well. In fact, we found that 30% of the time, or 30% of the frame are going to be removed on average, and this will save about 30% of CPU. In terms of bitrate saving, we're about 10% bitrate saving for HEVC and 5% bitrate saving for HEVC, which natively handles better all the redundancy than HEVC. Now, can we combine some other methods that we discussed this morning? The answer is yes, again, and we're going to look at combining dynamic resolution encoding and dynamic frame rate encoding. So here, we see that for complex content temporarily, we're going to encode at a lower resolution, but high frame rate. In this example here, on average, encoding at 540p60. This will use mainly dynamic resolution encoding, provide a lot of CPU saving, and some quality of experience improvement. For temporarily simple content, first with HD content that will be encoded at high resolution, but low frame rate. And we'll use the dynamic frame rate encoding, saving a lot of CPU and with same VQ. For SD content, it will be encoded in HD, in 1080p, but low frame rate. So this one will use both the DRE and DFE, provide mostly no saving, and the quality of experience will be, on the other end, much better. Finally, to summarize of the benefits of these three methods, dynamic encoding style, dynamic resolution encoding, and dynamic frame rate encoding. The encoding style and the frame rate both provide bitrate saving, significant for the encoding style. The quality of experience or VQ improvement is mainly brought by the resolution encoding. CPU saving are brought by the DRE and DFE. And in terms of interoperability, the dynamic encoding style and the dynamic frame rate are for all applications, transport stream and HTTP, whereas the dynamic resolution is mainly for HTTP, meaning OTT. So we've seen these three examples, which are quite different, in fact, and show how AI can, in fact, revolutionize the video compression. The work that has been shown here took only a few people and took a short period of time. It would have been much, much longer using legacy methods. We have an exciting future ahead of us because this is just, we're just starting. And we have been using the improvement for only parts of the codec. And we could use it in full parts or many parts or even the full codec. So this is future work that can be done. In a more general term, for video compression products, we can expect to use artificial intelligence also for bug corrections. The machine will be able to detect automatically bugs and make some corrections. And also, finally, and very interestingly, machine learning or artificial intelligence can be included into the video compression standards. There are already several applications or several proposals for VVC, the versatile video coding, that will be issued mid of next year and include at the moment some proposal with artificial intelligence. So as you can see, we're just starting. As Jan LeCun would say, this is just the icing on the cake. We still need to work on the cake for video compression. So thank you very much for your attention. This is just the beginning. Have a great SMPTE conference.
Thank you very much, Jean-Louis. Again, questions, if there are any from the audience, we've got a microphone in the center corridor. I see someone getting up, and please state your name, affiliation, your question.
Josh Derby from Discovery. Jean-Louis, two quick questions. What picture quality model did you guys use when you were setting up your VQ? And how, when you did your frame rate decimation, did you avoid changing the motion appearance and the apparent shutter angle?
Okay. I'll answer the first question. I'll re-ask you the second. I'm not sure I got the second question. Yes, the video quality measurement is a very important topic, and we have our own, in fact. This is a video quality tool that we have fine-tuned over the years, that it's proprietary, and it's definitely a key aspect of the success of this technology. And I'm not sure I got the second one, sorry.
So on the second one, when you decimate frame rates, you change the motion appearance, and you can change the apparent shutter angle of how the picture looked. How did you avoid that effect when you were decimating frame rates in your encode?
So again, here we look at the VQ, and visually we make sure that there's no visible degradation. Yeah, if there's degradation, we keep at the high frame rate. Yes.
Hi, Laura Perez from HBO. Was quality of experience the only measurement you use for the video analysis? And if so, why?
We use only what analysis?
Quality of experience?
Yes. So here, when I use the term quality of experience, sometimes it meant video quality in terms of no artifacts, no mosquito noise or such things, or it meant also higher resolution, for example. So,
Okay, so what measurement did you use for, like, to know what degradation you were having in the video? Because right now there's, like, the quality of experience is a measurement that you can find in many equipment that give you, like, a percentage, a value that you can know if the video is good enough or not. Mm-hmm. So what measurement did you use to know if the degradation was not that bad?
Mm-hmm. Yeah, here it's about the visual quality, in fact. Yeah.
Okay, thank you.
And I had a question for you. What about player clients? Are they ready for these rapid changes in resolution and frame rates, or is that going to take a couple more turns of the cycles for those devices to be ready to do this?
Yes, this is also a very important question. Thanks, Thomas. So right now, that's why of the three methods I showed, there are two which are applicable to all delivery methods, and one of them is only for OTT. The dynamic resolution selection or encoding applies mainly only to OTT, because not all terrestrial or satellite receiver are able to cope with that. The others, we have to generate the bit stream in such a way that it is compatible, and it is. But it's an extra work that have to be done. Yeah, sure.
Okay, well, thank you very much, Jean-Louis.
Thank you.